Today, we're going to talk about an element that is just full of incredible contradictions. I mean, it's the foundation of all life as we know it, but if you look in the Earth's crust, it's actually pretty rare. It can form the hardest substance we know and at the same time one of the softest. We are, of course, talking about carbon.
So how in the world does it do all that? How can this one single element be the backbone for everything from a brilliant diamond to the lead in your pencil to the very molecules that make you, well, you? This is a fascinating chemical puzzle, and we're going to solve it together.
All right, first things first, we have to really get our heads around just how fundamental carbon is. And it's no exaggeration to say this. Without carbon, life as we know it just flat out wouldn't exist.
And here's our first big clue in this whole puzzle. Take a look at these numbers. Carbon makes up a teeny tiny fraction of the Earth's crust and atmosphere. Yet it's the foundation for pretty much all life. That's a classic case of incredible impact from incredible scarcity, which tells you right away, there's got to be something uniquely special about this element.
This right here, this is another huge clue. Just look at the difference. Compounds made with carbon tend to have low melting points, and they're not great at conducting electricity. That's the complete opposite of a lot of other compounds. It's a massive sign that the bonds holding carbon atoms together are just built differently. So if they're not forming ions by giving and taking electrons, what exactly is going on?
And that leads us right to the heart of the mystery, the secret of the covalent bond. The answer to carbon's amazing versatility isn't about what it takes from other atoms, but what it shares. Okay, so here's the core problem for a carbon atom. It's got 4 electrons in its outer shell. Now, to be stable and happy like the noble gases, it wants a full shell of 8. So the two obvious options are, right, either gain 4 electrons to fill up the shell or lose the 4 it has. But for carbon, neither of those is a good option at all.
Think about it. If it tries to grab 4 more electrons, its little nucleus with only 6 protons just doesn't have the muscle to hold on to all 10 electrons. The whole thing would be unstable. But on the other hand, trying to rip away 4 electrons would require a colossal, just an insane amount of energy. So carbon's stuck between a rock and a hard place. Or is it?
And here is the absolutely elegant solution. Instead of fighting a losing battle to either gain or lose electrons, carbon does something brilliant. It compromises. Carbon shares its 4 outer electrons with other atoms, forming these incredibly strong and stable connections we call covalent bonds. It's a strategy of cooperation, not conflict, and it unlocks a whole world of possibilities.
Now, this unique ability to share electrons gives rise to 2 incredible properties. I want you to think of them as carbon's chemical superpowers: tetravalency and catenation. So, first up is tetravalency. It's a fancy name, but it's a simple idea. It just means carbon can form 4 strong bonds at once. Think of it like having 4 hands, making it an amazing molecular connector. But the second superpower, catenation, that's where the real magic happens. This is carbon's unique ability to bond with itself over and over and over again.
Honestly, the best way to picture catenation is like building with Legos. Each carbon atom is a block that can connect to other carbon blocks, forming these incredibly long and complex chains, branches, and even rings. No other element in the periodic table can do this nearly as well as carbon. It's in a league of its own.
So what happens when you combine these 2 superpowers? The ability to form 4 bonds and the ability to link to itself endlessly. Well, you get a nearly infinite family of different molecules. You basically get a whole universe of shapes. You can have straight chains, branch chains, even closed rings. And it gets better. Carbon can form single, double, or even triple bonds with itself. When a molecule has only single bonds, we call it saturated. It's like a bus that's full, holding as many atoms as it possibly can, which makes it really stable. But molecules with double or triple bonds are unsaturated. They've got empty seats, which makes them more reactive and ready for chemical action. It's a true molecular architect. Let's just watch this in action with a simple family of molecules, the alkanes. You start with 1 carbon atom, you get methane, that's natural gas. Add another carbon, you get ethane. A third one gives you propane, like in your grill. A fourth gives you butane for lighters, and on it goes. Each step just builds on the last, creating this predictable, growing family. That's the power of catenation right there on display. And the complexity doesn't even stop there. Because carbon is so flexible, you can have molecules with the exact same chemical formula, the same number and type of atoms, but they're arranged in completely different shapes. These are called structural isomers. It's exactly like having the same set of Lego bricks, but using them to build two totally different models.
Now, get ready for this, because it's mind-blowing. This structural variety doesn't just apply to compounds, it applies to pure carbon itself. These different forms are called allotropes. In a diamond, every single carbon atom is locked into a rigid 3D web with 4 others, creating the hardest substance we know. But in graphite, the atoms link up in flat, hexagonal sheets that just slide past each other. That's what makes it soft and slippery enough to write with. Think about that. The exact same element gives us the world's hardest gem and pencil lead, just by changing the arrangement.
And just when you think it can't get any weirder, it does. Meet fullerene, or C60, where 60 carbon atoms link up to form a perfectly hollow sphere. It literally looks like a tiny molecular soccer ball. It just goes to show the incredible creativity of carbon's bonding.
Okay, this is all fascinating chemistry for sure, but let's bring it all back home. Where do we actually see these carbon superpowers at work in our daily lives? The answer is literally everywhere. A huge number of our fuels are carbon compounds. When those stable, saturated hydrocarbons burn, they produce a clean, blue flame. Think of a gas stove. But the more reactive, unsaturated ones, they often burn with a smoky, yellow flame because they don't combust all the way. You know that black soot you sometimes get on the bottom of a pan? Yep, that's incomplete combustion of a carbon fuel.
All right, here's another everyday miracle brought to you by carbon chemistry. We all know soap and water gets rid of greasy messes, but have you ever stopped to think about how it actually works? The secret is a very special kind of carbon molecule. Okay, so the secret is this two-faced molecule. Soap is made of these long carbon chains. One end is the hydrophobic tail. It hates water, but it loves oil. The other end is the hydrophilic head. It loves water. So when you wash your hands, the oil-loving tails dive in and grab onto all the grease and dirt. Then, the water-loving heads all face outward, forming this tiny bubble called a micelle that traps the dirt inside. Then the water comes along and just washes the whole bubble away. It's a brilliant little molecular trap, all thanks to carbon.
So, what does this all add up to? What's the final count? Millions. Thanks to its superpowers, we know of millions of different carbon compounds. Let that sink in. That's more than all the compounds from all the other elements on the periodic table, combined. Carbon is, without a doubt, the undisputed king of chemical creation.
From the fuel that runs our cars, to the food we eat, to the very DNA inside our cells, carbon is the quiet architect of our entire world. Its unique talent for building this endless, stable variety of molecules is what makes life as we know it possible. It really leaves you wondering, though, if carbon is the basis for our life, what might life based on another element, like its close cousin on the periodic table, silicon, even look like? That's a question for another time.